Yeah, so let's start. We have already seen four assignments, and today we are going to see assignment 5 of last year's course. So I will solve first eight questions, and tomorrow Shubhajit will solve the rest seven. And so let's start. Shalmi, you can see my screen?
Yes, sir.
Okay. So I think you have already seen the question, and probably you might have already started trying it. So it says, let F be a free group on the set X, and N is a natural number which is fixed, and H is a subgroup generated by the all nth powers of the elements of F. So is the following statement true or false? The statement is whether H is normal in F or not. So maybe if you want, you can try for some time, or you have any hint how to do that.
Sir, actually, I don't get these concept on फ्री ग्रुप एक्चुअली मैंने क्लासेस भी ज्वाइन की है बट मुझे ये अच्छी तरह से समझ में नहीं आता फ्री ग्रुप का
Okay, so first definition is simply this कि a group which has no non-trivial properties, just group के axioms follow हो रहे हैं,
यस यस
उसके
वो
अलावा और कोई non-trivial relation नहीं है. Second फिर इसका construction जो है that comes from by defining equivalence relations. वो वाला part देखा था and equivalence classes.
यस सर पूरी वीडियोस देखी हैं मतलब कैसे वो दो नंबर ए बी लेके उससे बनाते हैं वो वर्ड्स का सेट बनाते हैं फिर इक्विवेलेंस क्लासेस बनाते हैं वो वाला फ्री ग्रुप बनता है बट जब हम इसको क्वेश्चन पे लगाने की सोचते हैं तो समझ में नहीं आता कैसे लगाना है इसको देन वो यूनिवर्सल प्रॉपर्टी जो इसकी होती वो भी समझ में आ गई बट इसका एप्लीकेशन नहीं करना आता ये
See, whenever you are working with a free group, first of all, uh, just try to use the basic prop four axioms of group, nothing else. Order भी आपको पता नहीं है इसका. Order of course infinite ही होगा if you are not imposing any non-trivial relation, because order is a non-trivial relation. X, if you are saying some for any generator x, x raised to n is identity, so that's a non-trivial relation. तो ऑर्डर भी इसका इन्फिनाइट मान के चलना है. सो नथिंग मोर देन दोज फोर ग्रुप एक्सियोम्स. इसके अंदर आइडेंटिटी है, इट इज क्लोजर, इट हैज एसोसिएटिव प्रॉपर्टी एंड इट हैज इनवर्स, दैट्स इट. और वो भी आपको पता है हाउ द ग्रुप ऑपरेशन इज. ग्रुप ऑपरेशन इज सिंपली एडजॉइनिंग, राइट? यू पिक टू वर्ड्स एंड देन उसके बीच में ग्रुप ऑपरेशन क्या होगा, जस्ट एडजॉइन देम. फॉर एग्जांपल, आपने एक्स वन एक्स टू एक वर्ड लिया. Okay, so let me try to write something. So just starting with a, a free group on two letters. Okay, say F2 is generated by your X1 and X2. So uh, group operation is just adjoining. Is for any W1 comma W2 in F2, what W1 star W2 is, it's just adjoining. You write W1 and W2
यस सर
simultaneously. Okay. So for example, uh, say W1 is your x1, x2, x1 raised to some cube, or x2 raised to 5, and your W2 is just um, x2, uh, x1, x2, 4, something like that. So W1 is star, W2 will just is just put them
एडजॉइनिंग
together.
Yes.
And definitely you need to cancel or add powers because that is under the equivalence classes. Okay. we, so it will, the power of x2 will add at the end, otherwise it's same x1 x2 x1 cube x2 6 x1 and x2 4. So this is the group operation. Identity is your empty word.
Yes, sir.
Identity is just your empty word, and inverse is also uh,
प्राइम वाले नंबर
what?
मींस जैसे x1 x2 है तो x1 प्राइम x2 प्राइम लिया था उन्होंने
Yes,
इनवर्स
yes.
को
Hmm. So inverse is your W inverse, such that if your W is say some x1 I1 x2 I2 x1 J1 x2 J2, then your uh, I'm just working with some examples, although I know you already know this. So your
यस
W
सर
inverse will be, just take the inverse of all this x1 x2 J2 inverse, and then follow the horseshoe property. It will be just x2 inverse J2, and then so on to x1 inverse I1. And as you said, x2 inverse is denoted by x2 dash. It's raised to J2. Then you have after x2 you have x1 J1. So it will be just uh, x1 dash J1 and x2 dash I2 and x1 dash I1. So an associativity is already there. Closure is also there. Okay. So
यस सर
closure and I closure uh, is follows from the equivalence property, right? Uh,
यस सर
closure and associativity is also there. So whenever you need to work with the free groups, then just keep in mind that you have only these four properties, nothing else, until unless some relation is imposed that you have a free group uh, modulo certain relations, then you can use those relations, otherwise you have nothing except these four properties. That just keep that in your mind. For example, if you are let's see the question now. So it says it's a free group on the set X, and H is a subgroup generated by the nth powers. So mm, now let's coming to the question. So this is to here. So you have given H to be x raised to n, such that x belongs to f, and f is just uh, to denote that I forget the notation, ऐसे डिनोट किया था free group on
एस
x. In the question it is x, so I'm just changing it to
यस
x.
सर
Free group on x. Okay. So now we need to prove that it's normal. So for normal, we just need to check, we need to check whether that in the question it's given that we need to check h normal in this f of x, or whether g h g inverse is again in h for all g in your g, that is your f of
Free
x,
group.
and yeah, h, small h is in your capital H. So that's it. Uh, Now whatever we are given about h, we will just use that, nothing else. So h is just the set of powers. So we will start with an arbitrary element. Let h belongs to your capital H. Then what is the possibility for h? H has to be some power. H is some
Some,
k raised to n, right? For some
yes, sir.
k in f, on f, right? Okay. And before that, I just want to add one more thing. That x is, let's give some notation to its generators, x1, x2, so on to x raised to r. Okay, so x contains these elements. So k is an element in f, so k has to be a word in x1, x2, so on to xk, right?
Yes, sir.
So for some k belongs to f such that your k is a word in x1, x2, so on to xr. Okay, let k is of this, say x1 I 1 comma 1, x2 is I 1 comma 2. These integers may be 0 as well. Okay, but we can write any element in this form, x3 some I comma 1 comma 3, so on to xr I 1 comma r. Then again you will start with x1 I 2 comma 1, x2 I 2 comma 2, so on to xr I 2 comma r. And this sequence will end at some point, because in words we are considering the finite sequence only. So again, some x1 I t comma 1, x2 I t comma 2, so on to your xr I t comma r. Okay, so any element you can write in this form. In this, see, yes, I need to write this also, where this I u v belongs to z. Okay, for all u comma v, right? And just try to understand this step. If you pick any word, then it has to be a sequence in x in the generators, right? It may be x1 dash or x2 dash, but you can say x1 dash is just x1 inverse. Okay, so if you are allowing these indices from the z, then it take cares of those x dash, right? Dash, it take care. Xi dash is same as xi raised to minus 1. So if you are allowing the indices from z, it will take care of that, and these indices may be 0 as also. For example, you pick uh, say k is your anything, x1 square, x2 cube, x1 inverse, or say x3, then uh, it is just x1 square, x2 cube, x3 0. If it is in f3, okay, uh, then you can again start with this x1 inverse, x2 0, and x3 raised to minus 1, right? So any element is of this form. Wherever some generator is missing, you can put power to be 0, and uh, okay, this x1 inverse I should write x dash, okay, because that notation you are following. So x1 dash can be replaced by x1 inverse, right?
Yes, sir.
Here it is one not dash. Let's follow. Shalini, is it clear right now? Up to now, it's clear.
Yes, sir. Clear.
Okay, so I'm just taking an arbitrary element of this f. It is looking weird, but to work with arbitrary element, we need to do that. Just try to show the entire screen. Okay. Now we have picked an arbitrary element of h. We need to check that whether its conjugate is inside the.
H.
Yes. You want to say something?
No, sir.
So let G belongs to F. Then we need to check what is G, GH, G inverse. So GH, G inverse is nothing but G. Then H is K raised to N, and K has this weird looking expression. Okay. So I need to write all these things again. So this is x1, x1 comma 1, x2, I 1 comma 2, so on to xr, I 1 comma r, x1, I 2 comma 1, so on to x r, I 2 comma r, then again dot 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 dot. At the end, we will get x1, I t comma 1, so on to x r, I t comma r, and it raised to some n. Okay, this is our conjugating. This is our conjugate. So now you can write it like this. Mm, this is same as just a minute. G x1 I 1 comma 1, so on to xr I 1 comma r, dot 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 x1 I t comma 1, dot 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 xr I t comma r, G inverse raised to n. So I can take this G and G inverse inside the bracket. And why this happening? Because you can see A, B, A inverse raised to n is again is same as A, B, and A, A inverse. You can see it's very trivial, because when you take the A nth powers, this A inverse will cancel this A again and again. Only the first A and the last A inverse remains. So it's A, B, and A inverse. So I am just doing using that and taking this G and G inverse inside. Okay. Now, what is this? Is it an element of F?
Yes, sir.
Yeah. Yes. Good, Ravi. This, whatever is inside this part, and starting from G to G inverse, this element is inside your F, because G is inside F, and all xi's are all also inside your F. So this this it's just a product of elements of F now. So whatever is inside, that is inside F. Okay. So this simply belongs to H. You agree? Because it's a power of an element of.
Yes, sir.
Okay. Shalini, I haven't used anything related to free groups. बहुत easily हो गया क्वेश्चन ये.
Yes, sir.
uh, by the definition of H. Okay. So in fact, this thing should follow for any group, because we are not using anything specific. It is following for free group. It will follow for any group. Let's see the proof once again. So H was just a set of all nth powers of elements of F. F is a free group on X. Uh, we need to check whether H is normal in this, or whether G inverse is inside H for all G inside free group on X and H inside H. So let X is the generating set for this free group. So for any H in H, H is some power of and H is nth power of an element of F. So such that K is a word in these many generators. So K can be written in this way. Now for G belongs to F, G inverse is just G times Kn times G inverse, and it is, by our assumption of K, it follows that this is Kn, and then you can take your G and G inverse to be inside, because AB A inverse raised to n is A B n A inverse for in any group that follows. So that's it. It's an element of F, and we have proved that G inverse is some power of, is nth power of an element of F. So G inverse belongs to H. Okay, and this will implies this, that H is normal in your F. Okay. So if there are any doubts, you can ask. Otherwise, we will move to the next question.
Clear, sir.
Okay, Ravi, are you getting?
Yes, sir. Proceed, sir.
Okay, ठीक है. So I will do the question number 2 at the end, because it's based on universal property, and I will just revise it once and then we will do it. Other questions are very easy, so let's handle them first. So, and here you don't need anything from free groups. Okay. So it says consider the group G such that G is generated by A and B, where A4 equal to B square equal to AB square equal to identity. So you have four options. How which one is correct? You can try for some time. See, here uh, it's just the group generated by AB is your free group on two letters. Now it imposing some more conditions. So then it's not a free group on two letters. Shalini, did you
Yes,
get
sir.
it? Okay.
Yes, sir.
So now it's not a free group. It has some more relations. And even after just putting some relation, the group might become finite also. Free groups are not finite, because their order of each element is infinite. So even the group generated by a single element gives you an infinite subgroup, because you can't impose the conditions related to orders. So, but this group may be finite.
Yes, sir.
Have you seen this kind of group before? Are these relations similar to
Uh,
something?
I think it is D4.
Yes, you are right. So uh, the solution is just this. G is isomorphic to your D4, or sometime people say D8, or maybe
D8.
I can write in it depends on which book you are following, which notation it has. So I'm just writing it in the form of 2n. Okay. So because 2n has this representation. In general, your 2n has is generated by uh, it is generated by rs, such that rn equal to s square is equal to rs square, that is equal to identity. Okay. At some places you might see this relation in a slightly different manner. They also say that this relation is same as uh, rs s r inverse, but it is also that also implies that rs square is identity,
Yes,
because
sir.
s is equal to s inverse. So you can take s it this side, and that will give you rs square is equal to identity. So G is isomorphic to D4 or D8, whatever notation you are following. So now you can answer the rest of the question, that as it is isomorphic to D4, so G is a non-abelian group of order 8 which has a cyclic normal subgroup of order 4, which is thus the group generated by its rotations.
Yes, sir.
Yeah, this cyclic normal subgroup of order 4. Okay, and that group is precisely the group generated by all rot. Yeah, group not generated, because if you are saying we are having all rotations, then generated doesn't mean anything, because they are the only elements. So it's just group of all rotations.
Yes, sir.
Group of all rotations. Okay, so this one was easy. The next question is easy too. Same question, just a small change in the relation. Here you have a raised to 4, and here you have a square. So this group also you have seen somewhere. Just try to recognize it. Ravi, have you seen it anywhere? Just for your hint, I can say that it's a group of order 8. What other group of order 8 you know?
It is a billion also. A billion बनेगा ये. And it is
It is abelian. Ravi, what you say? It's abelian or not? Mm, it's not abelian. Here you are
no,
not
sir.
given.
It is not a billion. Sorry, I have
It's not.
used.
It's not given that these three are equal to identity.
Yes, sir. Yes, sir. I have made
Okay.
mistake.
If it would have been given, then it would be just Klein's 4, right?
Yes, sir.
If a square equal to b square equal to ab square equal to identity, then it would have been a group of order 4, which is isomorphic to Z2 cross Z2. But it's not given that uh, it's equal to identity. So it's a non-abelian group of order 8, different from D8.
Q8.
Yes. So it's just Q8. Let's see how we can prove that it's Q8. So you can check that Q8 is generated by I comma j such that your I square is equal to j square is equal to ij square, which you also name at as k. Okay. Q8 as a group can also be written like this na, I 1 minus 1 I j minus I minus j, then ij and minus ij,
Yes, sir.
right? So it has the same property as your G. It satisfies I square j square equal to ij square, and no other property is required to define Q8. All other properties will be take care once you have these properties. Okay. So from this we came to know that G is isomorphic to your Q8, and thus Q8 also has a group normal subgroup of order cyclic normal subgroup of order 4,
Yes, sir.
which is what's that group is? What the
Generated by I.
hmm? Yeah, maybe I or J, anything you can take.
Yes, I or J. Which?
Yeah. So D4 and Q8 uh, are not same in the manner that D4 has a unique uh, subgroup of order 4, but Q8 has two different subgroups of order 4, or you can say
Oh,
three, generated by I, generated by J, and generated by IJ. Okay, so G is a non-abelian group of order 8, which has a cyclic subgroup of order 4. Okay, now let's move on to the fifth question. So it says uh, a square equal to b square equal to ab square, same relations. Then what is b cube a b ab cube a? One method is you know that this group is q8, you see what this relation, what is this in q8, or without even using that the group is q8, you can directly get it. See, at least from the given options, it is clear that the correct answer is of the form b raised to I times b cube ab a b cube a is some b raised to I raised to times a, right? For some I in natural number, right? So, and this can also be written as b times b square, or b cube times a b a. B cube a is same as your BIA. So what does this implies? This implies that your ABA is of you just need to find what is your ABA, and it has to be some power of B. This is just a hint. You all agree?
Yes, sir. Why?
Sometimes we can easily guess the answer through the options available. So it's I'm just using that. We will try to prove it without having anything known about these options also, but it's just one way of doing it. That you know that all options are of the form bi raised to a. So take the powers of b of present in the left side apart, and then a whatever a is there in the right, then you know that this a will cancel out with this a, and then you have this aba has to be some power of b. Okay, and that is easy to see from the given relation. You have b square to be ab square, right? We have b square equal to ab square. So this is ab ab. So this power of b will cancel out with this power of b. That will simply implies that aba is your b, right?
Yes, sir.
Now put it back to the given element ab, aba, b cube a. So this is b cube, b, and again b cube, and then a. So it is equal to b7. Okay, so that's already an option there. Now, if we don't know what are the options, that is having, without using the idea of known options, simply without using options. How you can do that? That also, see, if you are not given any option, then first of all you can write it in this way also, na, because it's also an element of G. So at least something would be given in the option, but it may be some option they might have given as 8 times b5 or 8 times b6 or 8 times b7. Then it would be more confusing. But here it is all four options are very nice. So that we can do. So that what I mean, that without using options. Anyway, option has to be there. Otherwise, you can't. Then the question doesn't make sense. It's an element of its own. So then if you are not giving any option, if they just write like g is this, then b cube ab cube a is what, then it doesn't make sense, because it's already an element. To to which element you are going to compare, at least some option should be there. So but here all options are nice. It is of some b raised to I a. So what I mean that without using options, that if you are having some more options and you don't know that which kind of element is this, then you need to do it by directly using your relations. So see, this AB and this ABQ, you can put this B cube, you can write this B cube as B times B square, then it will become AB square times B square A. Okay, so you are having the element as B cube ABA B cube. So it's B cube A, B, A, B cube, and then A, which is same as B cube, A, B, A, B, B square, A. Now this is in your simplified form. This is mm, B cube, AB square, B square, A, which also I like to write it as B times B square, AB square, then B square, and then I should write it like this. It's B times B square, A, B whole square, then B square, and then A. Once you have this, then all your relations are uh, in this form: B square equal to A square equal to AB square. So now you can use your relations as per the options available. Okay. So if the options are too bad, then you can guess all possibilities once you get this nice form. Okay. So after that, we can use the relations to check the options. Okay. So I hope the point is clear why I did uh, like this, because now see they might have given you as b a square, then ab square a cube. That is also equal to this element, because you can replace any b square by a square. So if the option is b a square, ab square, a cube, then that option is also correct. But luckily you are not having those complicated options here. So in general, if you are going to handle these questions, then try to set up in a in a form such that you can use relation in whatever way you want. Okay, I hope you
Yes, sir.
understand. Okay.
Yes, sir.
Okay, okay. So now let's move to the next question. So it says that let G be a group and AB is not identity, such that A7 is identity and AB inverse is B square, then find the order of P. This kind of question is very common. I think both of you might have seen this in many algebra books. If you have already following some book, either it's an exercise or in example. Generally, in place of a raised to 7, we have a raised to 5 in books. But if you are having a raised to 7 equal to identity and with the same relation, you can solve it in a similar manner. So maybe you can try it for 1 or 2 minutes. I will anyway give you the solution. Do you want to try it?
Yes, sir.
Okay. Let's try it for 1 or 2 minutes. So how to start? A7 is identity. AB A inverse is B square. So if we take the square of this identity, or let's say this will give you B4 is same as b square raised to square, that is b a inverse whole square. And I already told you that this is same as ab square a inverse, because the intermediate powers of intermediate a and a inverse will cancel out. Only whatever power is outside, that will come over b, and a and a inverse will be as it is. So b4
Yes,
is
sir.
same as a b square a. Now put the value of b square again, since your b square is ab a inverse. Therefore b4 is a ab a inverse a inverse. So it is just a square b a minus 2. So you can see that somehow we have increased the power of a. So if we want to use this a7 equal to identity, we need to take this power to a raised to 7. Then this will be cancelled out, and this inverse power of a will be cancelled out. You will have some power of b equal to some other power of b. Then you can uh, try to obtain the order of b. So we need some to follow this process until we get a7 equal to identity. So either you can do the same thing, square it, and then it will you will get a cube b a minus 2 and so on. Or simply you can now if you have the value for b4, so you can take its eighth power probably, or fourth power. Yes, fourth power will be good. Yes, so that is, you have the value for a b4, right? That is a square b a minus 2, a square b a minus 2 4. Again, the power is just the conjugate of b with powers of some power of a. So it will be just a square b4 a minus 4. This is b raised to 16, and you can put the value of a4 from the above, that is a b a minus 2 a minus 4. Okay. Mm, so you get a4 b. Oh, I'm missing something. It is minus 2.
Yes, sir. E raised to
Okay.
the power minus.
Yes. So b a minus 4. Here also it should be minus 2. This is minus 2. So now we have got till a raised to 4. We know that if we take the fourth power again, then it will be b raised to 16 times raised to 4. That is a4 b a minus 4 4, and that is a4 b4 a minus 4, and that is from, again by putting the value of this a4 b4, we will get a square b a minus 2 a minus 4 a6 b a minus 6. See, each if you are having b4, then your power will be increased by 2. If you are having b square, then your power will be increased by 1. So now we need a7. We will just raise it to power 2, b64 raised to square, that will be a6 b a minus 6 whole square, that is a6 b square a minus 6, which is, and that is what, b raised to 128, and it is a6 b square is ab a inverse. So it will be a b a inverse a minus 6, so it is just a7 b a minus 7. Now as your a7 is identity, a minus 7 is also identity. This is b128 is identity dot b dot identity. Since your a7 is identity, so that will implies b raised to 127 is identity. Now, does it implies,
128.
is it?
Oh no, cancel out.
Yes. Okay. So maybe I can write more clearly on the next page. This will imply b128 is b, that is b127 is identity. Does it imply that the order of b is 127?
No, sir. Order will be divisor of 127.
Yes, this implies order of b divides 127, but 127 is a prime number.
Yes, sir.
Is a prime number. So order of b is either 1 or 127. Since you are already given that b is not identity, okay, so order of b cannot be 1, thus its order is 127. Therefore, as b is not identity, therefore order of b is 127. Okay, this question is very common in many small exams. You can see this question, this kind of question again and again. Generally, you find a raised to 5 equal to identity and ab a inverse equal to b square, and what is the order of b. The process is same. Okay, if it would have been a raised to 5 raised to identity, then we would have tried to make it a raised to 5 b a minus 5, and here you would have some power of b. Okay, so idea is similar whether you have a raised to 5 equal to identity or a raised to 7 equal to identity. The order of b will change accordingly, definitely. Okay, uh, but sometimes they might make this question tricky. uh, if the final uh, power is not a prime, then it's a bit tricky. So there you might find an options like what is the possible order for b. Okay, like in the assumption, if there is no mention of whether b is identity or not, then you need to write both the options, that order of b can be 1 or 127. And if in place of 127 you are getting some other uh, number which is not a prime, then there may be more possibilities for it. Okay, that then it depends on what options are available and what conditions, what extra condition is given in the question. Okay, so but here it's just 127. Okay, then let's move to the next question. It says that g is the group generated by x comma y such that x raised to 5 y cube is x raised to 8 y5 equal to identity. Find the order of g. So this question is very easy because some powers can be directly cancelled out. If you cancel powers from here using this equality, what will you get? This will implies x cube x cube y
Y
square
square
is identity.
equals to identity.
Yes. Now this will implies that x5 y cube is same as x cube y square equal to identity. Again use the first two, that will imply x square y is identity, and that means y is x raised to minus 2. Okay, so y is some power of 2. Now uh, the initial relation x5 y cube equal to that will become x5 x minus 2 raised to cube, that is x5 x minus 6 x inverse, and we have that this is equal to identity. So we will get x inverse is equal to identity, that will implies x equal to identity, and y which was x minus 2, that will also be identity. Okay.
Yes, sir.
Okay, so the group generated by identity is nothing but
Trivial group.
trivial group. So it will implies order of G is 1. Okay. Next question is of the same nature. The answer is same, but it's a bit tricky. So first of all, I will say that for your convenience, sorry, you can assume that the group is finite because it's a numerical type answer. So anyway, you have to fill a finite of number. So you can assume that G is a finite group. Okay. Once you assume that G is a finite group, then all its element has finite order, right? This will implies order of y and order of x is finite. But uh, you are given that we have y cube is x inverse y square x, right? What does this mean? This mean y cube is a conjugate of y square,
Yes, sir.
and when two elements are conjugate, then their orders are same,
Equal.
right? And that will imply order of y cube is same as order of y square, and let's say it is your m. Okay. Now what you can say for about the order of y? See, y is y cube times y minus 2, so that will implies y raised to m is y raised to 3m y raised to minus 2m, which is identity. So order of y divides order of just simply m,
M.
right? And anyway, uh, y square raised to m is same as ym raised to square, which is we have already seen. Oh, oh, oh. Yeah, we can just say that this is equal to identity because mm, instead of m I should write order of y. So you have y raised to order of y whole raised to square. So that is identity square, that is again identity. So this will implies that order of y square divides order of y. And this is true in general for any n. Order of yn divides order of y. Because we are not using anything, right? Especially for 2. If it is yn raised to oy, then y order of y is raised to n is e raised to n, that is e. So order of yn divides order of y for any n. And this will implies that m divides order of y. Order of y square is m, na? And order of y divides m, and order of y, m divides order of y, both combinedly implies that order of y is m. Okay, so when this can happen, this implies order of y and order of y square is m. So this can only happen if and only if you have uh, this 2 does not divides m. Because if m is divisible by 2, then order of y square has to be m by 2, right?
Yes, sir.
Uh, and you also have order of y cube to be same. This will implies that 3 does not divide m, right? Now, if you take any prime, or this z is as a group is generated by 2 comma 3. So if just a minute, this z is being generated by 2 comma 3, because see, you can write one as one is uh, one belongs to this, the generator group is there, right? Because one is just 3 minus 2 belonging to 2 comma 3. So z is generated by these two elements. Now what? Let n is any integer. Mm, and I should write let n is, because at 1 it's going to be there, and n belongs to a set of natural number. So y raised to n is some k times 2 plus l times 3. This will implies yn raised to m is y square raised to km dot y cube raised to ln, which is again identity, right? This will implies order of yn divides order of we're missing something. Mm, 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 mm. So order of y divides m, and you can, using this you can also try to prove that order of im is just m. How? Because using the same trick. Or let me do it for you again. uh, y raised to order of yn, whether it will do, say, division
y raised to
of
power order of y whole power n.
okay. But it won't give you anything now. It will be just yn raised to order of y, which is which will implies that order of yn divides m, which we have already got.
Yes, sir.
Okay. So that doesn't make anything. So what if it's not m, it's strictly smaller than m? Then you have m by 2, 2 by 2 equal to identity. Let me contradict that the order of y square and y cube is identity, is m. I think so. Ynm is this. Oh, in fact, we don't need all these things. We can simply write ym raised to n and then its identity. You get this point? In fact, we don't need these things. We can simply write yn raised to m to be identity, because ym raised to m is y raised to m is identity. Just I'm connecting this generating set and all these things you don't need. For all n greater than 1, yn raised to m is identity, implies order of yn divides m. Now we probably needed to prove that for the converse part you probably need this. I did it in the rough, but I'm not remembering how I finished it. So maybe you can try. I will also try. What you will get that m is the same r. Wait, no. So 2 does not divide m, 3 does not divide m. Okay, so probably then any integer which is uh, bigger than 1 won't divide m. Okay, so that will say that m has to be 1, because nothing greater than 1 can divide m, so m has to be 1. Okay, you see, if this is required, then you can use this. Otherwise, without this also, I think you should be able to do. You just check with 5. 5 is just y square y cube, and their order of y raised to 5. Okay, order of yn is a divisor of m. So somehow this should imply that n cannot divide m. Now let's assume the contrary. If n divides m, then that will implies that n times r is some m. Okay, and then you have ym to be y raised to m raised to r, that is equal to identity, and which will implies order of y raised to m divides r, right? So if it is dividing m, then it will divide r also. Uh, okay, let's choose n to be a prime. Maybe then the situation might be a bit easy to handle.
Yes, sir.
Mm, So if n is prime, uh, then n divides m. That will implies that n r is equal to m. So ym is yn raised to r. So ym is identity. That will implies that order of yn uh, divides r, but order of yn is already a divisor of m also, right?
M.
Yes. So you can have order of y to be this side. This will implies n times order of ym times some t is your m. So here we are getting order of yn is m, but there should be some contradiction. It is dividing n is also dividing m. I'm missing something. This should give that its identity. I'm not sure how I did it, but you try it of your own. You will get that mm, m is not divisible by any prime. That's why m has to be uh, identity. Okay,
Okay, sir.
I will also try separately, and we will see if, in the next class, if you are not able to do that. If you are not able to do that, then we will see what again in the next class. So I'm just writing it that here that uh, this will implies m equal to identity, and that will implies the order of y is 1, and that is y is identity. Similarly, by similar technique, you can see that x square and x cube are also given to be a conjugate of each other. So use the same trick. The uh, order of x is identity, and that will implies x is identity. You will get G to be identity, just the trivial group, and then order of G is 1. Okay. Only catch here is to prove this. Okay, you try it of your own, because 2 and 3 generates the entire set of natural numbers. The entire group of integers that should somehow help us. So let's see the last question, which is in fact the second question, and uh, it's interesting. That's why I keep it at the end. So it says for a free group, it might not be visible. Now I think you can see it better. So for a free group F on set S of cardinality of finite cardinality, we define the rank of F to be the cardinality of the set S. Now let F be a free group on finite non-empty set X, and Y is any subset of X which is non-empty and proper. H is the smallest normal subgroup which contains Y. So which options are correct? Whether F by H is free or it's not free, and then what you can say about the rank of f f modulo h. Okay, so for that we will you have to use the universal property. So I'm just stating what universal property is. Universal property of free groups. So it says let f be a free group on S, and small f is a function from S to G is a function it is G is also a group, some group. Then there exists a group homomorphism, a unique group homomorphism such that G from S to this is
Free group 2K.
here I'm using S notation. You might be following the same notation as the lecture, right? So it is the free group over S, which is here I'm denoting it by F. So from here to here, you have the injection map, that is, say, J, and S to G, you have the given map F. So from free group to this group, there would exist a uh, group homomorphism. Let's say let it be denoted by F bar, maybe, because it will depend on your F. So F bar such that this diagram commutes. transpose with this J is F. Okay, this is universal property of free group. If you are following the lectures, you already know that. So you need to use this
Yes, sir.
property. Yeah, you need to use this property to actually uh, prove this. And I can just give you some hints. So you have the set. You need to take the set X, set minus Y. Here you will have the same thing, free group on S. Now your S is X, free group over the set X minus Y, and this X minus Y is not empty because Y is proper. Okay, and it's not and that's why they have assumed that Y is non-empty. Oh, sorry, it's proper. Okay,
Yes, sir.
and here you have you need to take the group F modulo H. Okay, so uh, yes, we need to define the functions as well. So here it's the injection this, and there you have some F. We need to define this F. What is this F? And corresponding to that F, we will have some induced group homomorphism F delta. Okay, so what F you can define? Okay, first of all, let's see what happens here. Here an element small x is mapped to the class of x in free group, and thus you have f o j of any x is f over class of x, and that is by the above relation is f of x. Okay,
F of X.
yeah. So I use the same color here. So it's f delta. Now we need to define this f. Okay, to define f, let x is the set x1 comma so on to sk, and without loss of generality I believe that y is x1 to xr. Without loss of generality, y is x1 x2, because I can order my x accordingly, right? R is less than k, city less than k. So x minus y will be x r plus 1, x r plus 2, so on to xk. ठीक है. Now your f will be defined like this. So f from x minus y to f modulo h is such that f of x I is just x coset of h with xi for all I belonging to this indexing set r1 r plus 1 to k. Okay, this is your function f. So you get a group homomorphism. You will get a group homomorphism from free group over x minus y to f modulo h, and you need to prove that this group homomorphism is a isomorphism as well. Okay, that I leave to you. Okay.
Okay, sir.
Prove that f tilde is an isomorphism. And Shalini, for that you need that f is a this capital F is a free group. It's free from any relation. So while proving that it's an injective, this f delta is injective, you need that this capital F is free group, because if it's not injective, then it will have a non-trivial relation. Okay,
Okay, sir.
so ये अभी क्वेश्चन खत्म नहीं हुआ है. So this will implies f x minus y is isomorphic to mm, f modulo h. So this will implies f modulo h is a free group, and rank of f modulo h is rank of, or is just the cardinality of this x minus y, and which is q of x minus y. So used, don't get confused with this between this modulo and this set
Yes,
minus.
sir. Yes, sir.
Modulo is this and set minus is this. The direction of this line is different. So this is equal to cardinality of x minus cardinality of y. Cardinality of x was the rank of f, and cardinality of y was the rank of h. Okay, this will prove a general result. So f modulo h is free, that you have already proved. And the second part was, if cardinality of x is 10, cardinality of y is 6, then what is the rank of f modulo h? It's going to be 10 minus 6. Rank of f minus rank of h. So that is cardinality of 10, x minus cardinality of 5. That is 10 minus 6. So it has to be 4. Okay.
Yes, sir.
This implies if mod x is 10, mod of y is 6, then rank of f by h is 10 minus 6, that is 4. Okay, so that's it. If you have any doubts, then you can ask. Otherwise, we will stop the session here.
Thank you so much, sir.
Okay, thank you, Shalini. रवि, where are you? समझ में आ रहा है आपको?
जी सर, कर रहे हैं थोड़ा
हाँ.
थोड़ा.
So you are in MSc, or you have finished your MSc?
सर हमारा सिविल्स के लिए है सर, भारतीय सिविल सेवा के लिए है.
Okay,
यूपीएससी सिविल्स के लिए कर रहे थे.
okay, 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 okay. There you need all these things.
हाँ सर, ये तो ग्रुप फिर हमारा मैथ्स ऑप्शनल ही है ना, तो ग्रुप और रिंग्स तो
Okay,
है.
okay, 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 okay. So BSc आपकी होगी कंप्लीट, राइट? और ये MSc
हाँ
भी करी है?
नहीं सर, हमने बीएससी कंप्यूटर साइंस से किया था, मैथ्स भी था उसमें.
Okay, okay, okay. You can interact in between. जरूरी नहीं कि हर बार ठीक हो. uh, जितना इंटरेक्ट करोगे उतना ज़्यादा सीखोगे. ठीक है. Okay, then we will meet on next Friday. Tomorrow is Shubhajit's lecture, so you can also attend that. You should attend that because the next 7 questions will be solved by him, and then on the next Friday at the same time we will meet again. Okay, okay then we'll
Yes,
stop
sir.
it here. Okay,
Okay, sir.
bye.
Thank you.